Recently, we've been studying the reactions of pure benzene, most specifically, electrophilic aromatic substitution. That is where the benzene ring has its pi electrons, and its pi electrons attack an electrophile. We're going to look at how this would occur if we instead added a substituent to the benzene instead of using pure benzene. Now, the substituent can affect it in two main ways. It could either activate that benzene for its electrophilic aromatic substitution, or it could deactivate it. So that's the first effect that we could look at. And the second effect we're going to look at is which carbon on the benzene ring would be more likely to react. So which carbon on the benzene ring would the new substituent, probably end up on? So those are the two main things we're going to look at. Let's dive in and take a look. So if we look at our benzene, we can put two different kind of groups on it. First of all, we could put a group on it that donates electron density into the ring. That usually would have a lone pair right here, and it would probably donate down into this ring. Now, if we have more electron density in that benzene ring, it would be more likely to go attack an electrophile, compared to pure benzene, of course. Now, if we look and compare that to another substituent that withdraws electron density from the ring, that is going to deactivate it. Now we have less electron density in the ring, so we'd be less likely to attack an electrophile with that substituent there. So remember, one more time, this is for electrophilic aromatic substitution. We'll look at nucleophilic aromatic substitution at the end of this conversation. All right, so let's now look at our second effect. So that was activating and deactivating. Let's look at our second effect, which, as you recall, was direction. So if we look at the benzene with something attached to it, we're going to be asking which carbon on that benzene is the most reactive. So let's start by looking at something that has a lone pair that donates into the ring. Well, as we donate that lone pair down, if we draw resonance structures, we form a pi bond here. And as we draw our resonance structures, we notice that would form a carbanion on this first carbon that would get pushed around to the different carbons. So if we look, we notice we have a carbanion on 3 different carbons. And if we draw our resonance hybrid or look at a resonance hybrid, we'll notice that there is a partial negative charge on 3 different carbons. Let's look at an electron withdrawing group. Well, if we draw an electron withdrawing group, that is going to draw a pi bond out of the benzene ring. If we draw that pi bond out of the benzene ring, it forms a carbocation on that benzene ring. If we push our carbocation around by pushing around our pi bonds, we notice that carbocation is on 3 different carbons, actually the same carbons as that carbanion was. So the question now is, which one of these carbons would end up being more reactive? Well, remember, this is benzene acting as a nucleophile. It's attacking with its electrons. So the one that donates electrons to the ring, these negative points here are the ones that are going to be more likely to attack an electrophile. So if it donates electrons, it's going to be ortho and para directing, because we notice that we've circled the ortho and para carbons. If instead it withdraws electrons, what we're going to see is that these positives do not want to attack. That's not a nucleophile, right? A partial positive is the furthest thing from a nucleophile. So those carbons will not attack. So the ones that remain unchanged here in the meta directions are the ones that are going to now attack. So if we withdraw electrons, we have a meta director. Before we move on and put some of this together and look at some real examples, I need to make one note. And I'll make that note with a little bit of review. So if we review carbocations, what makes a carbocation more stable? Well, if we add groups to it, of course, remember it increased the stability. Well, what if we added a chlorine to it? What would that do? Well, this was an interesting example, if you remember, because we talked about how chlorine's very electronegative. So it's going to withdraw electrons from the carbocation. So we'd predict that it would make it much less stable by inductively withdrawing those electrons. It turned out then that we had a twist in our story. That chlorine also has a lone pair, and that lone pair can be donated up, stabilizing that carbocation by spreading the positive charge out. So we realized that that chlorine could both inductively withdraw electrons and donate via resonance. So what effect does the Cl end up having on a benzene? Well, if we draw a Cl on a benzene, we'll notice it's the same exact thing we've learned before. It's very electronegative, so it withdraws electrons from the benzene ring. However, it also has that lone pair, and that lone pair is able to donate and move that carbanion around to those 3 carbons. So what we'll notice is that it's actually being deactivated by those withdrawn electrons. And at the same time, the 3 carbons in the orthopara positions are the most reactive. This is actually the case for all halogens. So now let's dive in and look at specific examples of what these substituents are. What are some examples of these substituents? Well, the first one we'll look at is an amine. An amine has a lone pair on the nitrogen right here, and it also can donate that lone pair down. So that really strongly activates the benzene with donation of the lone pair. And alcohol is the same, and alcohol also has a lone pair it can donate down to activate that benzene ring. Now, what if we have a nitrogen here, but now it's part of an amide? An amide has that lone pair, but it also has a carbonyl. Well, that lone pair could donate in and activate the benzene ring, but it has another option. It can also move up as the carbonyl resonates up, which then it would not be donating. Because it has both options, it's only moderately activating, but still the lone pair goes down, so it is activating. This is the exact same situation that an ester is, because it can do the same thing. So both of those are moderate activators. Now let's look at our weak activators. So any alkyl group or any just plain carbon bond is going to donate a little bit by a sigma bond compared, of course, to a hydrogen, which is no substituent. But that is only weakly activating because there's no lone pair to resonate down and donate in that way. All of these activators, since they're pushing electrons into the ring, are all orthopara directors. So these would cause the reaction to happen at those 3 orthopara carbons. Now what about a halogen, such as, like we said, chlorine? Well, remember, it has very strong electronegative withdraw, so it's drawing electrons out, but also has that lone pair that it's donating down. Because of that, because of its strong electronegative withdraw, it's actually weakly deactivating. So it actually is different from all those orthopara directors and activators we just looked at. But interestingly enough, it is an orthopara director because of that lone pair donation into the ring. If you took a benzene ring and attached a carbonyl directly to it, remember a carbonyl has that resonance we've looked at many times before, where the pi bond resonates up onto the oxygen. That means that the benzene can donate a whole pi bond directly to that carbonyl, filling in that pi bond space. So that is going to be a really moderate deactivator. Pretty strong effect, actually, but we still call it a moderate deactivator. The strong deactivators are things that are positively charged. So a great example would be a protonated amine, or one other example we have is a nitrate. A nitrate is a really strong deactivator because that pi bond between the nitrogen and oxygen is able to resonate up, making the nitrogen positive and accept a pi bond there. So those are great examples of strong deactivators. So this kind of sums up all of these different examples that we can see.